So this is what we're going to spend all 10 weeks on, linear systems, AX equal to B. And of course, you know, you could say what's special about this, because even though if you're doing MATLAB, you could just say, that was kind of trivial. I just hit that backslash and I got the solution, right? And so what's so special about what we're doing here? Well, part of what we want to do here is start thinking about more broadly when we come to this. I mean, you know, most problems are always going to come down to this, right? So that's the thing. You take a very difficult problem, you start breaking down in pieces, and inevitably this is going to show up. And especially now in the data science world, this matrix A starts to look massive, right? It could be trillions by trillions. Like that's if you're large scale Google, Facebook type data. And you know, you want to think about how am I going to solve these kind of problems? And how have we done it in the past? How are we doing it now? How are we going to allow ourselves to do it at scale and computationally efficient manners? What we learned in linear algebra typically was do Gaussian elimination. And this is exactly what you don't want to be doing. Gaussian elimination is the slowest way you could possibly solve AX equal to B. Okay? So all we're going to be talking about in the class during this quarter is, well, you need some speed here. You need to figure out fast computational algorithms to solve this problem. Because when you have large-scale linear algebra problems, if you don't figure out how to do this computationally efficiently, then you're kind of in trouble. Okay. If you look at the website, I talked about linear algebra and matrix decompositions. So that's going to be the theme throughout, is this idea of matrix decompositions. And what I want to do through the quarter is go through all these different matrix decompositions. So what is a matrix decomposition? Well, it's to take that matrix A and potentially write it in a simpler form so that we can solve AX equal to B much more rapidly. Okay? So I'm going to list over here a number of matrix decomposition techniques. And what I'm going to show you is that with these matrix decomposition techniques, there are lots of advantages if you can decompose this matrix to solve the problem faster. Initially, let's start off with matrices A. And they can be complex numbers that are m by m's. Okay, they're square matrices. We're going to relax this in a bit. We're going to have to talk about what it means to have a non-square matrix in a little bit. But right now, let's just assume I have m equations and an, okay, let's do n by m, not m by m. Okay. Okay, n equations and unknowns, and this is what you probably had in linear algebra, and you figured out how to solve this. And typically the way we did this in linear algebra was to do Gaussian elimination. And Gaussian elimination, to solve this, I'm going to put this here. It's not a decomposition. It's going to cost you around, you can be more precise than this, but it's going to cost you around order n cubed operations. Okay? So if it's a small matrix, that's not a big deal. But part of what we want to do is go to big matrices. And you can see as you go to big matrices, you're cubing this thing. So this is problematic because, you know, if you're solving an 1,000 by 1,000 matrix, all of a sudden you're going to cost you 10 to the 9 operations. But what if you're doing data like you're downtown Seattle, you're at Amazon, Facebook, Google, and you have, you know, matrices that are billions by billions? Well, now all of a sudden this 10 to the 9 becomes 10 to the 27. You can see the problem. If you're doing this in data analysis, you're going to get fired. All right? That's just fact. Like that's, people will go, what? go get an education and come back, because this is not what we should be doing. When we do computational solves for this, our goal is to figure out how do we do these in fast algorithms and fast ways. Okay, so let's talk about different decompositions. The first one I want to talk about is called the LU decomposition. So what I'm going to list over here are the decompositions and show you how they work here. What the LU decomposition does is a matrix decomposition that takes the matrix A and turns it into a product of two matrices. The L and the U, the L is lower triangular, the U is upper triangular. Now, why would we do this? If we could find this decomposition, then you could say, well, if A is this, then what I'd really be solving is LU x is equal to B. Now I'm going to call this here Y. So I'm going to say that U of x is equal to Y. Then that means LY is equal to B. Now what I want to highlight here is what the decomposition did for us by having this upper triangular and lower triangular. I've broken it up into two problems that are n by n. But notice what I gained as an advantage. So what I'm trying to solve for is x, right? So that's going to be in this equation. But first I need to get y. Well, y I'm going to solve from here. I have L. Let's say if I could do this decomposition, I'll have L, I have B, so I solve for y. Now you say, well, that's still a big linear solve, but notice it's in lower triangular form, which means all I have to do is forward substitution to get all the values. And forward substitution means, so the structure of the L matrix, these are all zeros, and I have this times y is equal to some b. So, you know, y1 is equal to that number. And then some number y1 plus y2 is equal to this number. So you first find y1, put it in here to get y2, put it in here to get y3, and down this list you go. This will cost you order n squared operations. So you're just forward substituting to get y. Once you have y, you can come back up here, and u is upper triangular, which allows you to do back substitution to get x. So you're not having to do Gaussian elimination. You just forward or back substituting. That's also order n squared. So in general, like if I have this decomposition, what I've really done is I've broken it down into two problems that are order n squared, which the two you can throw out and just simply say that this is order n squared. This is a pretty huge savings. If you have 1,000 by 1,000 matrix, this is going to be 1,000 times faster, right? These are the kind of speed ups you're looking for in computation. It's these speed ups in computation that have allowed us to solve some of the grand challenge engineering and science problems of the day, like basically modeling airflow over an entire airplane. You need fast computation algorithms. These are the kind of things that you're using, okay? So the LU has this advantage. The question is, how did you get that LU? So we're gonna have to start talking about the cost of actually getting that. It turns out doing an LU decomposition costs you order n cubed, but you only have to do it once, because once you have the matrix factored, you can use it over and over and over again for different B values, okay? All right, so that's an LU decomposition. Hopefully this makes sense of why you would use it, because once you have it, all you have to do is forward or back substitute. So this is a classic matrix decompositions, okay? Used heavily in scientific computing. All right. That's one matrix decomposition. Let me give you another. And by the way, all these matrix decompositions, they were all made up to solve Ax equal to B. So, right, the fact that there's so many is that people have tried lots of methods to get this thing to work, okay? Or to try to improve speed. What are the kind of decompositions you come up with? QR. The QR algorithm, and we're going to spend quite a bit of time on QR in 2 weeks' time. What this is very much like LU, right? I'm going to take A and write it as a product of two matrices Q and R. Now what Q and R are is Q is a unitary matrix. Now what's awesome about unitary matrices, and we'll talk quite a bit about special matrices on Monday, unitary matrices are such that the columns are orthogonal to each other and they're unit length. So what's great about these matrices, the inverse is simply the transpose. Transpose complex conjugate, you're done. Because usually computing an inverse of a matrix is a very computationally intensive. Here it's trivial, okay? So there's really nice properties around unitary matrices, and we're wanting to use as much of the properties as we can of what these decompositions give us to take advantage of solving this for these solutions. The R is upper triangular. Okay? So notice, interesting, when we do these different decomposition techniques like LU, they represent U as an upper triangular, L as a lower triangular. When you go to QR, R is upper triangular. So they're not consistent in their terminology. But just, that's okay. Every decomposition sometimes calls these things something different. Just keep in mind that when you see a U, it doesn't mean it's always upper triangular. Because in QR, it's the R that's upper triangular. So let's talk about solving Ax equal to B with this. So now you have QRX is equal to B. We'll do something similar to what we did before. We'll call Rx Y. So what you have is Rx is equal to Y, and then you have Qy is equal to B. Okay, so it looks very similar to what we just did with LU, but there is a big difference. When I go to here, if I want to get the solution to Y, all I got to do, right, is multiply now by Q transpose. Q transpose Q, because it's unitary, is the identity. That's the fantastic part of having unitary matrices. So if I take Q transpose on both sides of this thing, Q transpose times Q is just the identity, so you get Y is equal to Q transpose B. So once I have this Q matrix, all I got to do, hit it with B to get Y, bring it into here, and that's upper triangular, so all I just have to do is back substitution. Okay, so to solve the Ax equal to B, I do one matrix multiply and back substitution. So just like LU is going to be an order n squared operation because I have to do this back substitution here. Okay, so that's why you might use something like this QR decomposition. It has orthogonal vectors here, upper triangular there, allows you to set up simpler systems to solve much more efficiently computationally. Okay, good. So there's another decomposition. Let's keep going. All right. So the fourth decomposition we're going to talk about, and this is one that I think everybody kind of knows. It's the eigenvalue decomposition. We often, that's the one thing we learn in linear algebra beyond just saying, you know, AX equal to B and do Gaussian elimination, learn some things about matrices, and then you might find some eigenvectors and eigenvalues. So the question is, how can you use those to your advantage in solving AX equal to B? Well, remember the eigenvalue problem associated with that is AX equals something like this. So I take that matrix A, the columns of X are eigenvectors, and this matrix here is a diagonal matrix with the eigenvalues. This is the eigenvalue problem associated with this. So these are all the eigenvectors, all the eigenvalues. The important thing about this, well, actually, let me stay consistent with my notes. Sorry. I'm going to call these eigenvectors, so I'm going to call them V instead. AV, so V's are the eigenvectors, those are the eigenvalues. What I'm going to do is multiply both sides by the inverse of V. So what this tells you is that A is equal to, that's the decomposition. Notice the difference. LU is 2 matrices, QR is 2 matrices, and now this eigenvalue decomposition, it's breaking it down into 3 matrices. Now notice that 2 of them are the same, right? V is there, but you're seeing V and its inverse both here. So this is your eigenvalues, eigenvector decomposition, or eigendecomposition, okay? So how could we exploit the eigenvalues and eigenvectors to do this decomposition? Well, let's go back to AX equal to B. So A now is this guy. So you have AX equals to B, but A now is B, B, okay? And so what you could say is, hey, how about if I call this thing here Y? And what you could do is multiply both sides by V inverse. So V inverse V, identity. And then you get V inverse B. Let's call that B hat or B hat. Yeah, so then what you would end up with is where this B hat is V inverse B. So what I've done is I've made a transformation. I've moved into eigenvector coordinates by making this transformation, and you ask the question, what advantage did I get by doing that? What I got is a new linear system of equations. But here's the awesome thing about this linear system of equations. What did I say this matrix was? It was a diagonal matrix with the eigenvalues. This is already solved then. It's in diagonal form. In other words, you know, this thing here is lambda 1, lambda 2 times y1, y2. So y1 is equal to b1 hat divided by lambda 1. y2 is b2 hat divided by lambda 2. I've got it all solved. Okay? And once I get this y, right, then I can just I can get back to x by multiplying by v. So the beauty of diagonalization is I actually just solved the problem already. I put it in this form where it's like get the entire solution out just because it's in diagonal form. By the way, for those of you guys with a physics background, also an engineering background, you know, one of the things that eigenvectors are always used for, this is why people really know eigenvectors or have experienced them in the past, is because a lot of these physical systems, one of the most important coordinate transformations to make is to put it in a diagonal framework. I just showed you how that works. I made a transformation to a new variable y, and in this new variable y, everything's diagonal, everything's easy. Instead of n equations with n unknowns that are all coupled, It's n equations that are 1 by 1s. That's the power of an eigendecomposition. Okay? So that's one possibility. Now, one of the things we're going to be talking about throughout is there's different reasons you'd use these. Eigendecompositions are fantastic. You can't always produce an eigendecomposition of a matrix. It's not guaranteed to happen. You have to have certain properties of a matrix to do it. Okay? So just keep that in mind, that that's the concept here. All right. Next decomposition. You know how Thor has his hammer? Mjolnir. Well, anyway, this is the Mjolnir moment. Like, we're going to pull this. This is the SVD, the singular value decomposition. In my view, this is the most important decomposition you need to know. I'm a little bit surprised that when you come out of a lot of linear algebra courses in undergrad, you've never heard of it. I never did. But to me, the singular value decomposition is one of the most powerful. It's one of the ones that, it's frankly, what, if you're going to pick one decomposition to know, it's the SVD. So SVD, singular value decomposition, and it's a product. It breaks the matrix up into a product of two unitary matrices and a diagonal matrix. Okay? We're going to spend all next week talking about SVD. It's one of the workhorse decomposition algorithms that people have come up with. It's fantastic. It really is an amazing, it's an amazing decomposition. Notice how close these are to each other. We're in fact make connections between eigendecompositions and SVD. The eigendecomposition in SVD looks similar, right? Look, three matrices, the middle's diagonal. But here's the power of the SVD. The eigendecomposition requires one set of vectors V, which are eigenvectors, here, and it's inverse there. So this is not two independent coordinate systems. It's the same one that you see both it and its inverse. SVD works with two orthogonal coordinate systems, right? This is a unitary matrix, which means all the columns are orthogonal, unit length. This is another unitary matrix. All the columns are orthogonal, unit length. Two orthogonal coordinate systems. It's that flexibility that gets you so much further than this constraint of having one coordinate system. Now, solutions then are going to look very much like eigenvalue vector decompositions. You're going to solve AX equal to B. There's your decomposition. A is this. I'm going to multiply both sides by the inverse of U, which in fact is just U star. Remember, it's unitary. So if I multiply both sides by U star, I simply get, and then I can just call this X hat and this B hat. And notice what I've done. So this is X hat here, that's B hat here. This is now a new linear system of equations, but this matrix here is diagonal. So I get the same thing I did with the eigenvector decomposition. It's in diagonal form. It's n 1 by 1 equations. Trivial to solve because it's in diagonal form. And I've moved myself into a new coordinate system where what I do is if I have this decomposition, I project X into the V unitary matrix. I project B into the U unitary matrix to create these new embeddings called X hat, B hat. And in that coordinate system, everything's diagonalized. Everything's independent. Every direction is independent of all other directions because this is diagonal. By the way, we'll go through this. I am guaranteed that the SVD will work for any matrix. Square, non-square, any matrix. Singular, complex, any matrix. Keep that in mind. Really important. Most decompositions work under certain constraints. One of the powers of the SVD, it doesn't matter. You just give me a matrix, it will have an SVD. Okay. There are a couple other ones, but we're kind of pretty close here to the time. One of them is called the Schur decomposition, and the Schur decomposition is restricted to square matrices. And again, it looks very similar to this, except for now, instead of the inverse, you do the transpose complex conjugate. That's the Schur decomposition. You can do that decomposition as long as it's a square matrix. And the other one that I'll list here, and these notes I'll send to you, is called the Cholesky decomposition. The Cholesky decomposition takes advantage of the fact that if A is symmetric, which is a pretty harsh restriction, by the way, right? There's not that many matrices that are square and symmetric. These are special matrices. But if it is, Cholesky is a really fast decomposition that people use to compute the solutions out of this problem. And it's, again, based exactly on these kind of concepts here. So, you know, here's 4 decompositions. Gaussian elimination, again, let me just say it, this is not what you want to be doing. When you do computing, you do not want to do the slowest computational method possible. You will get fired. And your science career will end, and your thesis will go on forever because you're solving a linear problem, okay, for 5 years straight, okay? Here, you're getting towards the power. Each one of these is built to go fast and solve things quickly and go to scale. And so there's 4 decompositions here. If you had Schur and Cholesky, that's 6. And there's more decompositions. But the number of decomposition tells you a lot, because the number of decompositions is telling you that people are thinking about decomposing matrices all the time. This is what you're going to do if you're going to do scientific computing, broadly speaking. Most problems are going to come down to this, to an AX equal to B solved somewhere. And so it's really important to have an appropriate decomposition at your disposal to solve it quickly. That's where we're going to end today. Let me map out what's going to happen Friday and Monday. Friday, we're going to come back to some really important linear algebra concepts. They're going to be review. Concepts of orthogonality. Concepts of when can you actually solve AX equal to B? What if A is not a square matrix? Right? We got to start thinking about that. And then on Monday, we're going to talk about special matrices. We're going to talk about what are the properties of unitary matrices? What are the guarantees around those kind of, what are Hermitian matrices? There's a lot of different matrices that have names and have a lot of special properties. And I want to make sure we kind of know what they are, list out the properties and the guarantees we have, because we're going to use these matrices all the time. And I want to make sure we set up the foundational structure right. And after that, we'll just go right into the SVD.